Okay, so that will take you probably to a territory that is probably new for many people, not probably very well mastered by the others. But fortunately, the only message to take is a very simple idea, and it's in fact a shame that this idea has appeared in a very tortuous way. Could have been observed by many people long time ago, but that's not how things happen usually. You know? So that's a contribution to the story how ideas arrive. You know? I'll talk about non-equilibrium states in models which are described by conformal field theory, one space, one time dimension. These will be states where you try to pre-impose the temperature and or chemical potential profile, which are not uniform. Okay? And well, there are many sort of systems whose low-lying excitations are described in one-dimensional systems are described by conformal field theory that usually concerns low temperatures and short distances. Well, there are sort of carbon nanotubes, there are sort of systems which are localized by potential walls, for example, in the interface between two materials. There are edge channels of Hall systems, or the one-dimensional chains like XXZ chain, for example. Let's go this way. Okay. So, well, it's for a long time has been known that conformal field theory, such systems can be used to describe their ground state and as well as thermal properties in the equilibrium states. But sort of recently, people tried to describe also transport and non-equilibrium, some non-equilibrium properties in such systems. Well, as you will see, they are sort of somewhat specific, but and maybe not the most interesting non-equilibrium phenomena, but still, I mean, it's nice to have situations where you can describe things exactly. These attempts to go beyond equilibrium physics using conformal field theory, they include so-called partitioning protocols where you prepared one-dimensional systems, sort of half-line systems in different equilibrium states, different temperatures, different chemical potentials. Then put them in contact and watch what happens. Well, there's sort of long history, but there are nice reviews about that in these issues of our Journal of Statistical Mechanics, which has very many nice things, in fact. So there is a review by Denis Bernard and Benjamin Doyon on this stuff. There are also studies of quantum quenches to short correlated states, which used conformal field theory that was sort of initiated by Cardi and collaborators. And again, there is a nice review there. And what I will try to add to it is a small sort of brick, as I say, but showing that conformal field theory may be also used to describe evolution of states where you try to impose profiles on temperature or chemical potential. So all I would be saying came out in discussions with those people Edwin Langman, Per Mosavi from Stockholm, Joe Lebowitz from Rutgers, and Vieri Mastropietro from Milan. They wrote a very nice paper, Time Evolution of the Luttinger model with non-uniform temperature profile, when they made an interesting observation. So, well, they considered a Luttinger model, which is a model of interacting one-dimensional electrons, let's say a rather good model of quantum wire at low temperatures and short distances, old model and stuff. And it's exactly solvable, both with local and non-local interactions of electrons. But with local interactions, it's also described by conformal field theory, very simple one, because by bosonization, it sort of reduces to one of the three massless bosonic fields, and you can sort of describe everything in this language. Well, so what they looked is the states which sort of formally look in as if you try to make a Gibbs state, but instead of using the fixed inverse temperature, you use a profile of inverse temperature. This is the energy density, okay, at time zeros. So that's a formal formula because you want it on the whole line. Okay, so you should go through the thermodynamic limit. I'll say a word about that. Probably I have time. And well, you look at profiles of this type. You don't require that they are monotonous. They can do whatever they like in the middle, but you want them to be at least asymptotically constant on the left and on the right, and you can take the same values, but more interestingly, you can take different values on the left and the right. Okay? So, well, so one of the things they showed, which is not very surprising, that on long times, if you start with such a state, it goes to sort of generalized Gibbs state, but that's a fancy name for something very simple. I mean, this conformal field theory has left movers and right movers. And left movers, well, it's a little bit a problem of terminology, but left movers which will thermalize for a long time in the temperature which is here, and the right movers with the temperature which is here. I mean, the Ness, if you want. Well, it's a generalized equilibrium because it's sort of there are left moving energy and right moving energy are conserved, so you can build a Gibbs state out of two. So the Ness is not very interesting. Okay, the dynamics will be more.
This is the initial condition.
That's initial condition. Okay, and then you evolve. So for a long time, you go to such a state which is not very interesting in a sense. Well, it's not interesting, but one of the things which you will have, it has a constant energy current. Okay? Just because, well, we'll come to that probably in a moment. But more interestingly, they showed the following thing. They calculated the expectation in that non-equilibrium state of energy density at time t point x and energy current, which is the same as the momentum current, at time t and point x, and got the following result. There are sort of two waves, one left and right, another one right moving, with a function which has a term which is proportional to temperature squared, and has another term which is expressed like that. Okay? And in fact, what they notice is that thing here is a Schwarzian derivative of a function f, which is comes from integrating the inverse, well, the temperature profile. Okay? So, well, immediately they sort of guessed that there must be conformal field theory behind that, because Schwarzian derivative appears in the transformation laws for energy momentum tensor. Well, and at that stage, I mean, they came to ask to me what the conformal field theory behind. I mean, sort of, and that's what I provided. I mean, okay, so this result implies that if you wait long enough, in particular, that then you get the energy density, which is a sum of terms proportional to temperature square on the left and the right, but also the permanent current, energy current, which is proportional to the difference of temperature squares. And that's not the first time such a thing was seen. Similar thing was seen in the similar long time stationary state arising in these partitioning protocols. Yeah. Well, more interesting what was happening in the time, earlier times. So if you look at the energy density, that's the energy density at time 0. Well, we subtracted the E0, the stationary value. Okay, so you see that there is sort of a bump like that developing at the beginning. And that's, of course, a phenomenon which was sort of discussed very hand-wavingly in these protocols, the partitioning protocols, that if you put such a states with non-agreeing temperatures, then at the beginning you excite a lot the sites close to the contact. And in fact here it tells you exactly how you excite them, at least, you know. And the problem with this partitioning things was that, well, I mean, the more abrupt is the bump, the higher peaks are here, you know. So if you really do a jump like that, if you're doing partitioning things, you of course excite the modes which are no more described by conformal field theory, okay? But then what happens, and that sort of tells you sort of within conformal field theory how you arrive there, okay? But then when you look at the next time, these sort of bumps start to separate into two. One goes ballistically to the left, the other one to the right. Is the red color. What are the other colors is when you put, as I told you in the Luttinger model, the interaction can be local or non-local. If it's local, it's CFT. If it's non-local, you put some dispersiveness in the model, some dispersion, and you sort of see that these peaks, the other colors are the green and blue. If it's blue, I don't see well. The peaks will diminish with time, okay, and become broader. In conformal field theory, their form is sort of stabilizes, and then they separate ballistically. So you see that this energy which are put at the beginning in the contact modes, okay, it sort of is evacuated ballistically from the system. Okay? As was expected, you know, in this partitioning protocol, okay, but here it's precisely described like, and well, technically, yeah. Well, that's, you know, that's the Fermi velocity, you know. So in Luttinger model, it depends on the couplings. Okay? You know, what creates those bumps is this term. Okay. If you don't put them, you won't have. You have sort of a smooth profile. Well, then if you look at the current, this is the current through the origin where you put the wall. I mean, and you see the initial that's time, and you see the initial surge of the current, okay, which is sort of bigger in local model, a little bit smaller in the non-local models, and then it goes from up down to the stationary value. And if you didn't have this term with Schwartz derivative, the curve would be this one. So that describes, the term really describes this, what these modes near contact do. Okay. Well, so I should have said that the way they arrived at this formula was pretty tortuous, because they sort of calculated these energy densities and currents in perturbation theory in Luttinger model in the difference between the left and right temperatures. So they started calculating. After sort of 3 orders, they realized that there is something arising. They calculated 4th order, then they sort of guessed this form, and then they worked hard to sort of show that the higher orders also fit into this formula. Okay? So here's the story how it comes from the conformal field theory. Let me start from a sort of short introduction to conformal field theory. So, well, I use as usually in Minkowski conformal field theory, you use the light coordinates, okay, that's the word. I use them like that, you know, for sort of obscure reasons. Then conformal transformation in 1 + 1 dimensional spacetime. These are just any transformations of left light coordinate and of the right. There are 2 different functions here. You can easily see that such transformation preserves the Minkowskian metric up to a scalar factor, which is exactly here. Okay? So that for sort of simplicity, I just take these functions which preserve orientation. You can go beyond that. I mean, if the theory would have such symmetry, but it's convenient to restrict to functions with positive derivative, sort of, rather than both positive and negative. So that's the Minkowskian conformal group of conformal transformations, and in quantum theory, it should be represented, which has the symmetry, will be represented projectively in the Hilbert space. And it means just that we have 2 commuting unitary projective representations of this group, F going to U of F and F bar going to UF bar. Bar means here another sort of whatever right moving. It's not a complex conjugation. Okay. So infinitesimally, these transformations are generated by the light components of energy momentum tensor T and T bar. So if you take diffeomorphism, infinitesimal diffeomorphism like that, then the corresponding transformation is identity minus the integral of energy momentum tensor with the vector field, which we have here, okay? Infinitesimal transformation. And then the energy momentum tensors component satisfy these commutational relations. The first part sort of means that they are really tensors of order 2, okay? Components of the tensor of order 2. And there is the central term here, which comes with the central charge of the theory. That's the coefficient C. Okay? And then what will be important for us, that the adjoint act, those transformation on the energy momentum tensor, well, the energy momentum tensor just transforms as a degree 2 form in the X, plus the central term, which is exactly the Schwarzian derivative of F with respect to X, with the combination of ratios of 3rd derivative and 1st derivative, and of 2nd derivative and 1st derivative. Okay, well, the formula essentially was before. And the same relations hold for the right movers, which. And in conformal field theory, the energy density and heat density, they come from summing the energy momentum tensors left and right moving, or taking their difference. So now suppose that you take a diffeomorphism, a function on the real line with positive derivative, who's just proportional to the inverse temperature profile. Well, in fact, to temperature profile, inverse beta. Okay? Well, and let's apply this transformation property to what we were putting in the exponential building this profile state, okay? So on that, of course, this is all formal, okay? Because I integrate sort of things over the line, and I also didn't really tell you what are the properties of f at infinity. I mean, we'll have to sort of think about that. But just formally, you go with this, this conjugation inside, you apply it to t, that spits out the square of the first derivative, changes the argument of t, and then there is the central term, which here we won't be much interested in because it's a C number. Okay? And in the state, we'll use this in the state where it will cancel, the C numbers will cancel between numerator and denominator. Okay, so now use the first, one of those first derivative, that's this thing. It will just kill the temperature profile, spitting out beta 0, okay? And the other derivative will combine to differential of f. Okay, so that allows you to change the variables, and you see that up to this constant term, you flatten the temperature profile. Okay. Just T is the energy momentum. That's why I don't use temperature. I use beta consistently for inverse temperature. Okay, so you see that the transformation did the job of eliminating the profile. Okay, so that whole thing essentially. You do the same for the right movers. Well, you have to use the function which is sort of related to the previous one by changes of sign, but it goes the same way. So when you put things together and you look at this thing you are putting into the exponential to build the state, so the integral of inverse temperature with the energy density, you apply the conjugation here. U will just only act on T, UF bar will act on this, and all together they will do the job of flattening the profile up to a C number thing. Okay? So you get beta 0 times Hamiltonian plus constant. Okay? So now if you sort of come back to the state, this non-equilibrium state with the pre-imposed temperature profile, well, you put these unitaries, conjugation with unitaries here and there. I mean, well, up to the thing that everything is formal because these traces don't really exist, but the ratio will. The unitaries cancel, so you can put them there, and these unitaries just produce beta 0 minus beta 0 h, well, plus constant, the same constant down there, so constant will drop, and you get relation between expectation of observable A in this profile state and the equilibrium state with temperature beta 0. That's the relation, okay? So that's essentially all which is there, plus the fact that I know how to compute such an observable if initial observable, for example, is built from the components of energy momentum tensor, because we had this formulae for the transformation of energy momentum tensor. And there is this inhomogeneous term in the transformation, the same for T bar, okay? So I know from those formulae, I will know what this beast is if A is like that, okay? And, well, similarly, well, in conformal field theory, there are sort of important class of fields, which are the primary fields, which really means that these are sort of fields which transforms as tensors under the conformal transformations. Okay? So, for example, their derivatives wouldn't be primaries, but these fields are tensors, because derivatives of tensors are not tensors, okay? Non-transform as tensors. Well, so usually they have the conformal weights, left moving and right moving, and under the conjugation, these fields will transform like that. I mean, sort of, the sums and difference come from the fact that we really transform the x plus and x minus, which are built by sum and difference t and x. Okay? So the Luttinger, in particular, Luttinger model with local interaction is an example of conformal field theory, which can be described in terms of free massless bosonic field with classical values taking compactified, taking modulo, really viewed as an angle on a circle of radius 2 pi r. Okay, and this, I mean, you won't see this compactification if you are in the ground state, but once you are in temperature states, I mean, you see, because it comes the winding modes of the field. Okay? And central charge is equal 1. Okay? The Fermi velocity also depends on the coupling, so there are two couplings which get translated ionization language into this radius and the Fermi velocity. Okay? And they have, of course, the energy momentum tensor as a conformal field theory in the local case. Local interaction case. They also have primary fields. There are electric currents, left moving and right moving, and there are Fermi fields, which, in fact, due to interactions, get anomalous dimensions. So they have these left and right conformal weights, which depend on this compactification radius, so depend on the coupling. Okay. Whoops. Well, then if you sort of add to this transformation, to this relation between the non-equilibrium state and equilibrium state, which we obtain, the fact that sort of in any conformal field theory, unitary conformal field theory, the expectations in the temperature state of energy momentum component, they don't depend on the insertion points, and that proportional to the temperature squared with a sort of universal coefficient, which has well, partly universal. It has the central charge and it has also the Fermi velocity for dimensional reason downstairs. So if you add to that and you use these relations between the states, in particular for the one-point function, you get exactly the formulae which were obtained perturbatively by resumming perturbation theory. Well, these formulae. Okay. And you sort of understand that this is really this term that really comes from this Schwarzian derivative, okay, and produces this, as I call them, heat waves. Okay, well, so the idea is terribly simple, and you know, I really think it's a shame that it wasn't noticed before. Okay? That it sort of came through this tortuous perturbative calculation. Things go like that. So it buys you those formulae. One of the things which you can get so from those formulae, you know, I mean, in this conformal field theory models, in those non-equilibrium state, the transport is still ballistic. You don't have diffusion. Okay? As a result, if you compute the thermal conductivity, I mean, in fact, if you compute it in frequency space, it will have a delta function in frequency with a weight which is called Drude weight. Okay? For historical reason, because you can get it from Drude model. And one way to compute it, you can compute it from Green-Kubo formula, but you can also compute it more directly from these non-equilibrium states where you take different temperatures on the left, on the right, the temperature profile, and it's just given by the expectation, non-equilibrium expectation of the momentum current, well, the term proportional to time for long times to it, which is selected by this limit. and then you take essentially derivative with respect to the temperature difference. Okay, and well, traditionally you multiply by beta 0 because you want rather derivative with respect to temperature difference than inverse temperature difference. Okay, well, so that you get for the for this weight of this delta function conductivity. This term, and in the local Luttinger model, there's nothing else. There's no smooth contribution to conductivity. The transport is really ballistic. Well, then of course, you know, beyond this one point function, you get all these sort of towers of equalities for the higher point functions, and I have to say that they haven't been really exploited. I wrote here a few examples, like for 2-point function of energy momentum tensor, for the current. Well, since the equilibrium correlation functions are known, I mean, you apply this formula and they spit out these things. Okay? For the Fermi field, I think it will be, and I think it's completely doable, and we haven't done it yet because it's all that pretty fresh. It would be nice to compute the evolution of the entanglement entropy in the interval around this kink, okay, of the temperature. And, well, you know that it will essentially, until the ballistic sort of heat waves go beyond this interval. After that, I mean, it will stabilize. It will be interesting to know what's the behavior before. Okay? And there are, well, these Calabrese techniques which permit to perfectly do it. But that hasn't been done. Okay? Well, then there is a similar approach you can apply, well, to the theories where you not only have the conformal symmetry, but also U1 current, like the Luttinger model. Okay, so if you have U1 current, which is in the Luttinger model the electric current or mass current, becomes essentially the same, which is conserved and which satisfies this relations, which essentially say that, well, this one says that J is a primary field of weight 1, 0, plus there is this sort of central charge, central extension relation for the commutation relation for two currents, the Schwinger term. Well, there's a little bit of freedom in how you normalize these currents, okay? And I will normalize them so that the spectrum of J is just in integers because electric charge is 1, okay? And then, well, this kappa becomes in the Luttinger model depends on the interaction. And well, so what you can do now is to do two things. You will do the previous thing, the conformal transformation, but you can also use the gauge group, okay, which commutes like that with the energy momentum tensor, like that with currents. I mean, there are these inhomogeneous terms with kappa. And you can use that now to flatten the temperature profiles and chemical potential profiles. In fact, you can, choosing this transformation appropriate way, you can completely get rid of the chemical potential. It's completely determined by things without. Okay? Well, and you crank the mill, for example, now with temperature and chemical potential profiles, you get this formula for the expectations, where there's additional term in the for energy density and current, which is proportional to chemical potential squared, and there are similar formula for the expectations of charge and density and current. Okay, and for example, you can get these Drude weights now for the electric conductivity. Okay? Well. that's essentially the story. Well, one of the things which you should think about is that I was completely formal in this manipulations. Okay? I was doing them in the infinite line without caring much. And I'm usually not sort of over sensitive to such questions, but here I think there is one important question, namely that I was using these conformal transformations which have different asymptotics. They are linear on the left and the right, but they have different asymptotics. So they don't compactify. Okay? And it's by no means clear that on the line they are unitary represented. Okay? So that was sort of bothering me, but there is sort of very nice trick which allows you to go around it. You just consider this conformal field theory on the interval, well, times goes up, the large interval, and you put special boundary conditions that there is no leak of energy to the left or to the right. I mean, there is no energy current through the boundary, okay? So, for example, for Luttinger model, in terms of Fermi fields, I mean, you have to connect the left and right moving things. You can do it like that brutally. That's not very physical. You can put Fermi momentum there, then it's a little bit more physical, but the result is the same. You get this type of boundary conditions. And then the theory becomes chiral. There's only one component of energy momentum tensor. The other one is completely enslaved. Okay. There is one representation of the diffeomorphism group. And now if you take this profile on the interval minus 1/2 of L, 1/2 of L, and reflect it, okay, to extend it to the left on the interval of length L, okay, you get a periodic profile. And in fact, you can sort of use the single transformation, the single transformation which has the derivative equal to the inverse of this doubled function, okay, to both accommodate transformation of left movers and right movers. Then everything is well defined, everything works, and you can sort of use the nice things of conformal field theory, which is essentially the modular invariance or covariance, to get the thermodynamic limit in a very slick and one-step way. I mean, so I won't go to it. It's a little bit sort of uses the standard conformal field theory techniques, but really make it very easy. So you first will go get in finite volume all these relations we had with the special conditions, and then by taking the limit, you get them in the infinite volume. Okay. Well, this is a thing about. I have just 1 minute. This is a thing about large deviations. There are sort of large deviations here the same way they were in this this partitioning protocol, as noticed by Bernard and Doyon. If you look at so-called full counting statistics of energy transfers, and if you look at this observable here, which we put in the state at the beginning, you can sort of think if the kink is sort of sharp, that it's a sum of energy on the left of the kink times left inverse temperature plus the thing on the right times energy. So if you measure it on 2 times, you get access to these energy differences, okay? And then you can get the whole statistics of that for this characteristic function of the PDF of those transfers. There is sort of formula which is similar as in this partitioning protocols or as in Levitov-Lesovic formula or whatever. I mean, so these are these 2-time protocols. And then you have a large time, large deviations. If you take logarithm of this characteristic function divided by t, you get this formula, which is exactly, the large deviations are like the ones in the partitioning protocol. And you can do the same with the, in Luttinger models, for example, with U1 adding the chemical potential. So we arrive at the end. So the main message here is that conformal field theory can be used to map in homogeneous situations to homogeneous ones, okay? So that's the whole trick, okay? The non-equilibrium situations we are putting our hand on here are somewhat, well, maybe not the most interesting ones, but still it's nice that they can be completely solved, also with chemical potential. Well, one can get exact formulae for this full counting statistical energy and charge transfers, for these Drude weights, maybe for the things like entanglement entropy, that's to be seen. Finally, Mosavi has observed that you can use the same trick to solve in the case that not only your state is inhomogeneous, but also you put inhomogeneity into the Hamiltonian, so into the dynamics. Okay. You sort of double this trick and you can still completely solve it. I mean, so that maybe can give rise to interesting applications too. Thank you very much. Conformal field theory. Anything with conformal can be described. So, you know, people did comparisons of these heat waves with the ones got numerically for XXZ model, which sort of on large scale is also conformal and has this sort of corrections, which, and there, because of these corrections, similarly as in the non-local Luttinger model, you see the dispersion and the slow sort of decay of these heat waves, okay? But for a long time, they sort of fit very well here, okay? So, yeah, absolutely. I mean, you can, with this doubling, well, having the both conformal and this gauge symmetry, you can do the same, exactly the same thing, flatten both temperature and the chemical potential. In fact, you can even get rid of chemical potential.
Generally, there's a relation. Does this hold also?
I don't know. Yet. I just don't know. We should compute this entanglement entropy, which is sort of standard but a little bit heavy computation. You get your replicas. Yeah?
For harmonic systems where one can compute by other means and one cannot compare, like for harmonic systems?
Well, you know, if you just take, you know, continuum harmonic system, I mean, that's certainly a conformal field theory to which, if you put it on the lattice, there will be these corrections, as in Luttinger, in fact, with non-local interactions, or if you put it on the lattice with slow dispersion. And I mean, well, of course, the harmonic case, the solution is sort of known. It doesn't mean that it's very simple, you know, sort of, and it's not very easy to read from the formula, but it's done for the discrete system. For the continuous systems, essentially the same thing. What I did here. One could make an exercise to show that the discrete one goes to that answer, but there's no doubt that it does.